Can record me having the last sip of coffee. Right. So I'm sorry that today the notes are not as carefully prepared, not as finished as last time. I only got down to write the things I would absolutely not commit to memory, namely things about toric varieties, so that I wrote down. But so for the rest, to avoid switching, I'll try to see if writing in real time on this thing works. If not, we'll just switch to the blackboard when we run out of space.
Yeah, why don't you just go to the blackboard?
Because different parts of the lecture are written here, and I cannot, as I said, I cannot keep them in my head. So I'd like to just show fairly quickly 2 slides that were left over from last time. Namely, I wanted to I'll return to the more interesting one, but everybody knows this one, I think. Oh, not everybody knows this one. And something's happening. All right, that kind of works. All right. So I firmly believe if you want to understand something, a class of objects, you better start with a point, I think. So pure gauge theory is a point mod G. You want to gauge a trivial theory. So the category that you get, well, the trivial category, you start with the category of vector spaces. That will give a trivial two-dimensional topological field theory. The invariance would be 1. I mean, the space for the circle would be the line C and so forth. And you start with that, you take fixed points, and we saw last time that the fixed point category is the category of representations of the group. Now the space you associate to a circle will be the Hochschild homology of this category, and that is well, there are 2 ways to compute it. One of which is by a twisted sector computation, and the other is, I guess, a direct computation. But what am I saying here? I'm sorry, just lost my bearings for a second. Yeah, the twisted sector computation tells you to take the sum over all group elements of the Hochschild homology of the functor induced by a group element on vect, and then in the resulting space take invariance, I wrote co-invariance here because it fits better, invariance under the entire group. Now all the functors are the identity. The Hochschild homology of vector with the identity is just C, so you just get a sum of copies of the line C with over the group elements G, and then you have to take invariance. It's slightly better to think of taking co-invariance, and then you well, if you take invariance, actually, I don't know why I switched. I'm sorry. Let's stay this way. This is a canonical statement of the G down there, but it's much more sensible here to take invariance. You get the class functions on the group. The other way to compute the Hochschild homology of the category is, notice that, just straight away look at that, and notice that it's the semi-simple category with isomorphism of simple objects being the representations of G, and you get in that situation a single copy of C in the Hochschild homology for every simple isomorphism class. So you get a direct sum of copies of C over the representations. So actually the little theorem here about twisted sectors, in this case, a slightly non-trivial theorem that, well, that class function, the space of class functions is in bijection with a span of isomorphism class of representations. The 2 different computations give you different forms of the answer. There's not very much to say about the theory. For a closed surface, for example, the path integral computation would produce the weighted sum of isomorphism classes of principal bundles of surfaces. You weight them down by the order of the automorphism group. Now, in this case, there's another way to compute the theory, because in 2 dimensions there are nice structure theorems about topological field theories defined by Frobenius algebras. And from those, you can give an algebraic computation of the invariance for a surface. And when you actually work your way through that, you begin to get identities because counting bundles in this way will involve counting conjugacy classes of tuples of elements in G with some relations between them, whereas the other computation, the structural computation, will involve dimensions of the irreducible representations. And if you compute the invariant of the sphere, for example, the two ways, you're going to get one of the standard identities in finite group theory. The way it comes about, I think, the algebraic computation comes about this way. This is a weighted number of isomorphism classes of principal G bundles on the sphere. It's only a trivial bundle and has G's worth of automorphisms. So that's what you get from counting. And this one is going to be the formula sum of theta v, I guess, to the 1 minus G, where the theta v's are the structure constants in the Frobenius algebra. And these are traces of the projectors. We come out to be dim v squared over G squared. So what I haven't told you, to actually do the algebraic computation, you have to make this category into a Calabi-Yau category. And you do it by specifying the trace. And the trace is going to be a natural trace on the representations, right? Every object in the category really is a vector space, an underlying vector space. So its endomorphism algebra is a matrix algebra as natural trace. And that allows you to define non-degenerate pairing between home spaces. So this identifies the Serre functor with the identity, this particular choice of trace. And this is the one which gives the identities. By the way, if you had to choose a different trace here, you'll be getting different invariants for surfaces, and you will not be getting a contradiction. You'll be constructing a theory which is not the weighted sum of isomorphic classes, but it's twisted by the Euler characteristic of a surface in some way. So, I mean, that maybe addresses the question of if you construct the theory a priori, is it going to agree with the one you want it to? Well, no, usually you have to make your choices correctly to get it to produce the invariants you want. So this is fairly elementary algebra. If you go to a compact, so it's surprising because of the compact group was even at the level of guesses, was spelled out later. Let's start with G, a compact group. So we just imitate the procedure. The category that goes with that should be the category of representations, finite dimensional representations. Well, you could interpret the twisted sector computation as giving class functions on G, but these are the characters of irreducible representations. So this is also the direct sum of copies of C over irreducible isomorphism classes. And that, of course, is a more direct computation of the Hochschild homology of this category. Again, it's a semi-simple category with infinitely many simple isomorphism classes now, but the Hochschild homology is still a direct sum of lines for each simple isomorphism class. So this heuristics actually works for now, so we're good. Now, the question is, what do you...
We are to think of everything as being an algebraic
Are we sorry?
We're using algebra. I mean, everything is algebraic.
Now G is a compact group, and this is a heuristic level argument only. So, but its category of representations is still a direct as a category. It's a direct sum of copies of vect, one for each reducible, just because every representation decomposes according to isomorphism type, underlying isomorphism type. So again, maybe this part could be vaguely algebraic geometric. This part, of course, is just heuristics in here, but it turns out to be the good guess. So we have to think a bit when interpreting the operation defined by surfaces with boundary.
Okay, why is this heuristic and before it was a theorem? Or?
Well, what does this is the compact group? What do I mean by?
Well, it's hard to
this?
say. Because you're not
Oh,
showing.
I'm sorry. Yes. this guy is a bit of a heuristic here, right? I mean, the direct sum of group elements of lines, and
That's not some kind
I'm
of
interpreting it as just functions on G, and this the invariants under G inside the functions. That's how it gets interpreted. And if you say algebraic polynomial functions, then you get exactly this. But if you said, for example, if you said continuous functions, you'd get some completion of this space, and then that would not be the Hauschen homology of that. So already it's you can see that there's some guessing involved in this step. And in fact, this is not exactly, not a perfectly well-defined two-dimensional DQFT, because the space for the circle is infinitely dimensional now. So strictly speaking, it doesn't satisfy the assumptions that allow you to construct a DQFT, and it's not a completely honest DQFT.
It's now the polynomial functions on G.
It's a polynomial class function, so the characters, the space of characters, and it's infinite dimensional. So, for example, because of that, if you ask what's the invariant of a torus, the invariant for a torus.
But there's something Calabi-Yau about it, or not?
Well, there is, because well. If you define, depending how you define Calabi-Yau in this setting, but if you define using a Serre functor, yes, there is one, because you do have this Hom Vida. You can again use a trace to give a non-degenerate pairing on Homs, and have Hom VW dual is Hom WV.
Okay.
And that's that. So, so it's Calabi-Yau in that sense. If you start looking at Lury's conditions, you'll find they're not met because the space is infinite dimensional. And for example, you pay the price somewhere. It's always going to be the case in topological field theory that the invariant, the numerical invariant associated with the torus, is going to be, well, a trace of the identity that on the space associated with the circle. Trace of the identity. So that's the dimension, of course. And in this case, that's infinite. So there is no numerical invariant going with the torus. Something funny happens that if G is the circle group, you have the same infinity problem with all genus surfaces. But when G is simple or semi-simple, the other invariants can be defined numerically and in a meaningful way. The reason why this still makes sense is actually this is a limit of a non-topological field theory, of Yang-Mills theory in 2 dimensions. And that's a theory that can be solved exactly. It depends on the metric, on the surface in a very mild way, it depends only on the area. And in that case, what happens for any surface, as soon as it has some area, for a cylinder, for example, as soon as it has some area, the operator from H to H, for which we're taking the trace here, the operator is no longer the identity, but it's going to be a trace class operator. It's going to be something like exponential. So the non-topological Yang-Mills, then if you have a cylinder with area A, then the operator is from H to H is going to send a line corresponding to the character of a representation V. On this line, it will act as exponential of the plus or minus, and apologize for that, plus or minus the area times the Casimir eigenvalue on V. So this has a quadratic decay in, so better be minus. Thank you. Has quadratic decay in the highest weight of the representation. So even if you have, when you form the sum of all representation, you take the trace, it's still going to be finite. So the non-topological, the geometric Yang-Mills theory in 2 dimensions, well-defined and finite, as soon as the surface has non-zero area. And the topological theory is the zero area limit of this geometric theory. So the non-topological is completely perfectly well defined. There's a Hilbert space of states. You can make this space in a Hilbert space in an obvious way, use the L2 inner product. The topological limit is a little bit iffy, but thanks to the fact that it splits up into a direct sum, we can still either compute everything we want to, or if it's not computable, we can tell right away that there's a problem. So in that sense, it's not too problematic. So, but let's go back to try to interpret, try to interpret the propagator for a surface with boundary, or if you prefer no boundary and you get a number. If there are boundaries, you must get linear maps between the spaces for the boundary components. So I think it was Witten who was first to point out, although the calculation behind it was done before, and I couldn't find in Wikipedia very quickly who's responsible for the prior observations. Physicist Mundell, no, yeah. Well, right. That's what happened to me. I think when I wrote it. Well, so in the finite group case, what we would be doing is we'd be fixing the principal bundles on the boundaries, so fixing the group elements that give the holonomies, and then taking a weighted sum over all principal bundles on the surface whose holonomies restrict to your choices. And that will give you a matrix coefficient of the map in the basis of conjugacy classes, basically of H. So the guess in that case that now, because you have a continuum of flat G bundles on the surface, the guess is that the sum should be replaced by an integral, and you get a kernel, if you like, for the space H, a kernel which gives you the map from one side to the other. I mean, if, at any points when you do the integral, you're going to get a function depending on the conjugacy classes. Use that as an integral kernel. And Witten's observation is that what you have to use is a symplectic volume on the space of flat connections, which is defined independently of a metric on the surface. And that gives a correct answer. It's not an unreasonable guess. If you were to guess something topological, that's about the only thing you have, actually. Symplectic. But it's actually a very surprising statement. Let me try to indicate why, and on Tuesday I'll make it precise why it's a shocking statement. And so what was known, and where the computation comes from, is that Young-Mills gauge theory can be computed explicitly by lattice approximation. That's a prior result. Migdal, thank you, yes. And if you do the lattice approximation of Young-Mills in 2 dimensions, it turns out to be exact, actually. So you don't even have to take limits and don't have renormalization problems. So what Witten did, he wrote a supersymmetric version of Young-Mills theory, and using arguments from supersymmetric quantum field theory, which I think to this day I don't completely follow, but they're perfectly sound, perfectly standard, I mean. They show that integral over the space of connection localizes in the topological limit to the locus of flat connections. So the path integral of Young-Mills theory, an honest geometric integral, in the topological limit becomes an integral of flat connections, and you further check that you get up to some rescaling, maybe a symplectic volumes. So that was his proof of the symplectic volume formulas, and at the time they were new, meaning people didn't know how to compute the symplectic volumes of the modular flat connections, and they did after Witten identified the theory coming from them with the theory you construct from the group. And the part that's shocking about this story is that what Witten is doing here, the topological limit of his Young-Mills theory, should be thought of as a twisted A model for gauge theory, the gauge theory for a point. Whereas the computation you do before from the category of representation is the B model, the gauged B model of a point. So what Witten actually proved at the time is he gave a B model version for a twisted version of the A model in the gauge theory of a point. So it's a twisted version of Gromov-Witten theory of a point mod G. That's what he's computing, and the answer turns out to be the B model for the point mod G. So I'll have to explain that I decided not to discuss this today because there are too many other things to bring in. So on Tuesday next week I will recall Witten's formulas, and I will explain this equality of twisted A model with B model at the level of categories. And that was the first indication that this techniques of looking at fixed points of group action categories actually can recover real things. And in fact, it was also caused a problem which had to be overcome, and that I'll start discussing today. So we'll return to this. I'll have to explain why that's a twisted A model. People who know a bit about know the language, or maybe you can see why this is a B model, because we're gauging the category of coherent sheaves on a point, which are vector spaces.
So what was the role in this of the statement that you can calculate it exactly on the lattice?
Well, you can calculate exactly on the lattice means you can actually calculate it. as a corollary, you can actually know the answer.
I see. That's why.
Right.
I see. So on the one hand, you know it's the symplectic volume. On the other
Right.
hand, now you know.
He didn't know the symplectic volume was not known at the time.
Okay.
So what he did is he showed that his super young Mills gives a symplectic volume. On the other hand, you could compute in terms of the old Migdal calculation of young Mills. So, and then he turned that into a rigorous argument for the symplectic volumes. For other cohomology classes, I'm not sure if I'm not sure if I could. If the argument he gave, it used some scaling limits which are a bit difficult to carry out. The formulas were made rigorous by other people for the unitary group by Jeffrey and Kirwan, and then further on, but with completely different techniques, of course. All right, so after this slightly incoherent leftover from last time, let me start discussing Lie group actions on categories a little bit. And this is interesting. So I'll just give a definition, some examples today, and then I'll move to the case of a torus for today, which will bring up an interesting problem in homological algebra, which I will discuss this afternoon. We'll have to learn that homological algebra and algebraic geometry, the way we knew it, is all wrong. We're going to see that distinct points can intersect. That's a great discovery in the subject, I think. But all right, let's go back to definition. So when you start letting Lie groups act on categories, there are two major branches, and I'm not talking now about the distinction between, say, continuous action or smooth actions or algebraic actions or so forth. I mean, on each side you can still make those further distinctions. And I'm just using the names from physics to discuss them. I'm talking about A model actions and B model actions. And the A model actions will be related to and come naturally from group actions on symplectic manifolds, and specifically their Fukaya categories. There are simpler examples from topology, which after the fact you can also interpret as Fukaya categories. It's has to do with the fact that we can interpret the modules of a cochains on a manifold as elements of Fukaya category of its cotangent bundle. So, stretching a bit, one could say that most examples are of this form. You can make up other examples algebraically. The B model actions are related to algebraic group actions on a variety and the resulting action on the category of coherent sheaves. And for the A actions, there will be two variations, and they correspond to the difference between D modules and flat vector bundles, or between flat connections and integrable flat connections. That's a distinction that appears if you allow infinite dimensional bundles. And D modules are, of course, a much more delicate story and they involve analysis or algebraic geometry, whereas flat vector bundles are much more basic. And I'll focus on the latter, topology. If you want to know more about action via D modules, probably David Ben-Zvi is a person to ask, because he and David Nadler have done quite a bit of work studying those types of actions. B actions are easier to describe. It's easier to say what it means. It means the obvious thing, basically. But I don't quite know how to fit it yet completely in mirror symmetry. I can only do it for a torus. Whereas in the case of A, I think I know a statement for any compact Lie group. So let's go back to the distinction already appears with vector spaces, but they're never called A actions and B actions. So let's see that case. So a B model action on a vector space, an ordinary action in the category you want, continuous, differentiable, analytic, or so on. It's a linear action. for compact Lie groups or complex reductive groups, the category of representation is semi-simple, and there is essentially no hidden information. I mean, if you want to become sophisticated and do homotopy theory and derived functors, you're not going to learn anything. Essentially, complexes with the G action will split equivariantly. So there's not much more than meets the eye in that case. Just representation theory of G, and that's all. Now, an A-model G action is an infinitesimally trivial or locally trivial action. These are the two variants I alluded to before. So that means you have an action of G on the vector space, and you ask either the Lie algebra action should be trivial, or that the neighborhood of 1 in the group should act trivially. And that's what I call infinitesimally trivial or locally trivial. And of course, for reasonable groups, there's no distinction, and either condition implies that the group only acts through its group of components, because the identity component has to act trivially. We like to keep the theorem that if a derivative of a function is 0 and the function is locally constant. When you pass to categories, actually, that begins to be a big difference. So that's why I wrote them separately. So nonetheless, even though it looks like we've reduced to the representation theory of finite groups, but that's not true, because now there's hidden homotopical information. And that's because the notion of homotopy trivialization, or the notion of a infinitesimal local trivialization or complex, can be softened up homotopically. So you can define it as follows. So let's say you have a complex of vector spaces on which G acts and commutes with a differential. And then instead of saying that the Lie algebra action is trivial as far as the eye can see, everything is trivial, you just ask that it should be homotopically trivial. And that means the following, that, well, if I denote by L psi the action of a Lie algebra element on the complex, the infinitesimal action, then I ask that for each psi in the Lie algebra should exist an iota psi, which is the linear map of degree -1, and which gives a null homotopy of the action of L. So the bracket with a differential should give you L. And in addition, I ask that the bracket of two of these xi's is 0. Okay, this is going to be the end of the notes for a while, and till we get back to ordered varieties. Time for a vote. Should I try to write on the dock camera or switch to the board? Okay, then there will be a official record. Well, not sure that's a good thing, but let's see if it works. So the conditions are familiar from differential topology. So the example of this, whoops. Let's see if it does too much of this. That might get difficult, I think, if it's going to keep doing that. Well, let's try a few lines. Good so far. So the example, X the smooth manifold, and G of course acts differentiably on X, and then we're looking at let the complex V, let it be the Durham complex, differential forms with the Durham differential. And then, of course, you have that G acts on everything. The Lie algebra acts by the Lie derivative. And if you define iota psi from omega k to omega k minus 1 in the usual way, that is by contraction with a vector field psi, then you have the Cartan formula, which tells you is exactly what we wanted. For Cartan formula, it exactly tells you that L psi is the supercommutator of D and iota psi, and it's obvious that the iotas supercommute. By the way, I always use a commutator to mean a graded commutator, so that means, of course, iota psi, iota eta, plus, in this case, iota eta, iota psi. Right. like that. And so you get an A-model action on the complex of differential forms. And you already know what you can do when you have such a thing, because well, what does one do with these things? That allows you to define or to give a model of equivariant cohomology. And what is equivariant cohomology? Well, topologically, if G acts on X, you can form a space, an equivariant space X sub G, that's the universal bundle cross X divided by G, that maps to BG, and maps with fiber X. And equivariant cohomology is the cohomology of this space. It's of course a module over BG, module, sorry. And you'd like to think of it as cohomology of BG with coefficients in the cohomology of X, but the coefficients are twisted. And the twisting is hidden in the G action, which has been locally trivialized, or homotopically infinitesimally trivialized. So the G action is non-trivial. G action on the cohomology of X, of course, literally is trivial, but the G action on the cochains on the RAM complex is only locally trivial, is only homotopically infinitesimally trivial. So even if G was connected, and you ask for a strict A model action, it would have to be trivial. So you'd only be computing the cohomology of BG with constant coefficients. And yet we know that you can find, if you take an interesting G action on X, the cohomology can have slightly more interesting features. So for example, if X is G with a translation action.
But I didn't get your remark about equivariant cohomology. You can calculate that from
You can calculate that from this
complex?
data. I'll write it in a second. You're right. Sorry, I'm getting a bit sidetracked. If you take G with translation actions, then XG is actually contractible. And the cohomology of XG, of course, is C with complex coefficient. That's, of course, not the cohomology of BG with coefficients in the cohomology of X. That would just be the two term of a spectral sequence. You forgot the differential. This converges to this guy. And what is called the Cartan model for equivariant cohomology allows you to compute the equivariant cohomology just from the data I wrote. So what you do is the following. You take your complex, omega xd. You tensor with, let's say, sim of G star, although some, and this is in degree 2. G star is in degree 2. So because it's graded, you don't have to worry at this point about power series versus polynomial. And you change the differential a bit. So the differential becomes differential plus the Cartan term. Let's call it psi a times iota a, where psi a is a basis of the Lie algebra, psi a is a dual basis of G star. So psi a lives here, and iota a is the operator we had just defined. And finally, take invariance under the group. And the proposition first is that D, maybe we'll call this D Cartan, DC from D Cartan, DC squared is 0 on the invariant part. Otherwise, in general, DC squared would be the summation psi a times Lie derivative by psi a.
Is there some model where these really are the forms? That thing you
But these are the forms on BG. Sorry, was it what you?
that big thing that you had.
Which
Whatever it
big-
was, you did something like G cross something, or X cross something with the G.
X cross the principal. Yes. So
I just wondered if those actually become
EG
forms.
cross X divided by G. So yes, there is a sense in which these are differential. These want to stand for differential forms on BG. But that's correct. Let me write in a second the answer. D squared is 0, so that's part 1, and 2, the cohomology is isomorphic to the equivariant cohomology of X. And the example when X was a point, to recover the statement, the cohomology of BG is just functions on the Lie algebra and invariants inside. So the invariant part are, if you like to think of it, the invariant part are the cohomology co-cycles, if you like. These are forms, but there is a very precise story which I'm not going to write down at the moment. Maybe I should actually. No, precise story which gives a model for forms on the space EG, which is principal bundle on the principal G bundle on BG, and the forms on BG. So this will be described in terms of symmetric algebra. This will be described in terms of the exterior algebra in addition to that, which gives the cohomology of the fiber. And they can be coupled by a differential, and that coupling imitates what happens exactly when you form the bundle, associated bundle of X over BG, and couple the differentials on the base to those on X. So you can do it universally in this bundle and then take invariants. There is such a story. And it has a name. Is it Weil model? Maybe Weil model for equivariant cohomology would cover it. And you can deduce the Cartan model then from doing the universal construction, taking the quotient by G inside. That's so the point of it is to define equivariant cohomology with coefficients. You need just these data and relation. Need to have a G action on the complex, need the homotopy trivialization of the Lie algebra action in this form, and then that gives you a coefficient system over BG in which you can take cohomology. For algebraic geometers, this is a little bit. See, to take cohomology with coefficients, ordinarily you would need a flat connection in the coefficients, in the vector bundle flat connection. What happens in this case, if you take the bundles of differential forms, there is a connect. We can put a connection on them on X. You can put a connection over BG, but it's not going to be flat. It's going to induce a flat connection on. Well, induce a trivial connection usually on cohomology, and what you get here is, well, it's like a bit analogous to what happens with the Gauss-Manin connection in the vibration of algebraic varieties, where, well, on forms the connection isn't flat, but the cohomology becomes flat. In this case, you can actually form a complex with a flat differential which squares to 0. So that's the analogy. So one thing I'll do on Tuesday is explain the analog of a Cartan model when instead of coupling to a complex, I'm coupling to a category. And that will be a computation of the fixed point category. And that will reproduce unknown results. So maybe another example of so we're still discussing examples of group actions on vector spaces. Oh no, let's stop. I think we've kind of covered the example. Every example is like the one I wrote. A complex with differential D and the homotopy trivialization of the Lie algebra action. I do have a comment, sorry. Comment explaining the relation, because it looks like a list of conditions and data and conditions.
Just in a word, what is the second example for us to think about?
The second example of?
The one you didn't do.
The one I didn't do. I just remember as an example for the next thing, not for this thing. But I come and explain the relations. So you have G, the Lie algebra G, mapping to the differential grade Lie algebra. Let me write it this way. Endomorphism of the complex V with differentials. This is the differential graded Lie algebra. Has the obvious commutator bracket and commutation with the differential. And how can you say a homotopy trivialization? So this is Yak map Elk psi, right? Well, a homotopy trivialization is a factorization of this map through the zero map, but only up to homotopy. You're factoring it through a zero space, but presented in a non-trivial way. So you're going to write on this side, so it'll be n0, I guess. Another copy of the Lie algebra in degree -1. You're going to write a differential here, which is the identity map. There's a map from the original Lie algebra to this complex. This complex is, of course, acyclic, so that represents a zero Lie algebra, if you like. And now what I'm asking is that I can continue to n-1. And this is the differential to a Lie algebra map. This must be a Lie algebra homomorphism. And let's spell out the Lie algebra relations here. So on G in degree 0, you have the usual Lie algebra relation, On G in degree -1, that is abelian. Brackets are 0. And G0 acts on G-1 naturally. And that makes me realize I forgot to write a condition. My data and conditions. G acts by G. This I psi is equivariant for G. So I'm missing. Where was the data? Oh, mysteriously disappeared. What? I didn't think one could erase the board in this context, but that's what seems to have happened. Now, well, there's a condition missing which says that the map I psi is also equivariant for the G action, group and Lie algebra action, without which things would not work, and that comes from here. So we're asking that the Lie algebra homomorphism from G to end of V should be factored to the zero Lie algebra. That's what the homotopy trivialization means. So factoring G to end V via the zero Lie algebra is a homotopy trivialization. But the zero Lie algebra, it's zero up to quasi isomorphism, and that's what makes the homotopy trivialization not an actual one. Right, -1. And the reason it's worth writing this to spell out this Cartan condition is because when we're acting on a category, the exact same conditions will come in for the A-model action. Okay, any questions? No questions, I see. So let's move on to categories. So definition, maybe that's red. So, well, the B model action is the easy one. So a B model action of G on a category is an action as a group. We define that for discrete groups, which preserve the structure you want. structure you want would be analytic, topological, continuous, smooth, or so on. Now, for this to be a definition, I'd have to tell you, define what it means to put a smooth analytic algebraic structure in a category and so on, which can be done, but it's extremely cumbersome, and Grothendieck taught us a long time ago how to avoid doing this sort of thing. So placing a structure on something is realizing it as a sheaf over some Grothendieck side. So for example, for a manifold, instead of saying X is a smooth manifold, look at the functor. So X, the smooth manifold, defines a functor on the category of smooth manifolds, represents it of smooth manifolds. So it sends Y into hom maps, I guess, of C infinity maps, we should say. C infinity of Y into X. And Yoneda's lemma tells you that you can recover X up to canonical isomorphism just from this set valued functor. The point is that these guys are now sets, so you don't need to remember anything about them. So for example, G, and I should, as a technical comment for people who know, this is a sheaf in appropriate topology. In an appropriate topology. I don't want to get into that kind of conversation. But then that means that giving a smooth structure to a category C is the same as, well, a priori just a category in sets, and now you want to put a smooth structure, so you don't just want the category, you want to enhance it to a functor on the category of, say, smooth manifolds. So converting it or enhancing it to a functor on the category, the Grothendieck side, actually. You want it to be a sheaf of smooth manifold. And then you can replace smooth with analytic, algebraic, or continuous, or your favorite structure. And then you don't have to start telling me what it means for objects to have a smooth structure, morphism to have a smooth structure, what kind of maps, submersion, so on. It's sort of packaged in there. Of course, you have to be able to produce that structure. And then G, if the appropriate form of G is also a group sheaf on the same category. So G is a sheaf of groups. On the same. And then saying that G acts on a category preserving the structure says that this sheaf of groups acts on this sheaf of categories. And structure preserving action of G on C is action of the sheaf of groups, action of the group sheaf on the sheaf of categories.
So when you say enhancing it to a functor on the Grothendieck side, you mean enhancing to a sheaf?
It's you enhance to a sheaf, yes. So of course, once I say sheaf, we're getting into trouble whether you want it to be strict or lax. And I think for categories, I can ask for strict, and then we don't even need to know what it means to be lax. And I'm told by authority that for higher categories, you can't do that anymore. But I'm not even trying to go there. And I should also say that, well, one thing you have when you talk about sheaves is sheaf cohomology, for example. So, and that's a derived functor of the functor of sections, and you can ask, do you have such a thing for sheaves of categories? The answer is yes. There are probably many ways to do it, but let's say that Joyal, based on all their work with Tierney, define a model structure on the category of sheaves over any Grothendieck side, on sheaves of categories categories over a Grothendieck side. And that's the thing that comes in when you want to talk about derived functors and you want to know they're canonically defined and don't depend on constructions. And there is a machine that does that for you in this case too. But so sometimes I might say derived global sections, and it means that there is a definition that guarantees there is a uniquely characterized object meeting those criteria. Okay. So we're done with the B action categories. I mean, of course, the example I mentioned have an algebraic variety with group action, then G acts in this sense on the sheaf of category of coherent sheaves. And that you can enhance to a sheaf of categories of over Y by saying that coherent sheaves on X applied to Y are coherent sheaves on X cross Y. That's the enhancement of the category. All right, so now let's look at A model action. So
that's the example we should have in mind, that coherent sheaves on X, but topology
yes, you make it in the sheaf of categories over the set of algebraic varieties in this way, yes. So you need to know what it means to have families of coherent sheaves parameterized by varieties, roughly. Intuitively, that's what it means to make it into a sheaf over some site. And that's what tells you what the algebraic structure is within the category of coherent sheaves. Once you decide what the algebraic families of sheaves are, you know.
So what's the example we should have in mind for a B model action?
Algebraic group acting on a variety, and it acts on its category of coherent sheaves in the obvious way. It's a strict action. You could play with twistings, but there's an obvious action there. So let's look at the A model action. And now there are the two variants I mentioned before. So first of all, we're going to say that G acts on the category C, structure preserving, and we'll pretend we know what that means. And now the structure, let's make the structure at least differentiable. And then I want to ask that the Lie algebra or the formal group G hat is a formal group at 1, the completion of the group at 1. So the action of G hat. So if G acts, any subgroup acts, including the formal group, that's really the Lie algebra. In other words, another way to say the Lie algebra. The action of G hat has been trivialized, possibly homotopy trivialized. Okay, so now we'd better spell it out, and there are several examples. So let me give an example first before I write the general condition. So maybe. So example. Can I give the example first? Let G act on the universal enveloping algebra of the Lie algebra the only way it can, by conjugation. And implied in it, I mean the action on G modules. So induces an action on modules over this algebra. So induces on the category of modules. So you could think of it either way, the action of the algebra or the induced action of the category. And I claim this action is infinitesimally trivialized, but we have to adjust our meaning of trivialized. Namely the action, so the observation is that the action of the Lie algebra is inner. Right? Because namely it's a commutator with some element in the algebra. So the action L psi, the infinitesimal action, acts by commutator with psi. And psi was an element in the Lie algebra. So if G acts differentiably on algebra, in particular the Lie algebra, like by derivations, and acting by inner derivations is a correct notion, or is one particular example of having the action trivialized. Because in particular will then act on any any representation of the algebra, because it will act just by, you can implement the action on any object. So that will give, so how should I say that? So exercise. This gives a natural isomorphism between the action, the induced action of G on U of G mod, on U of G modules, and the trivial action. A natural isomorphism between the action would have to be a map between an isomorphism between the destinations of the two functors, and the isomorphism will be done by observing that the infinitesimally conjugated representation is isomorphic to the original one, because you can let the Lie algebra element act. So in other words, it's a bit better to think of the Lie algebra as a formal group now. So if, let's pretend it was a group, if H was an element in the formal group, then the representation if H was an element in the formal group and V a representation of G, so an element in UG mod, then the transformed representation H of V would be the representation in which U of G act, but will first conjugate U of G by H and then let it act. So H of V is a representation where U in UG acts by HU, say the representation of HU H inverse. But now if the element H was actually represented on V, let's say internally on V, then the map from V to this H of V, then sorry, H of V becomes isomorphic to V by just I'm really mangling this up, sorry, I'm not.
By rho of H.
By rho of H, yes. Okay. Sorry, I kind of. So, for writing this, I've pretended that G hat was an actual group and had elements, which it doesn't. But what that means is that you can write this equivariantly for the Lie algebra. All right. So the point of the example, which ended up being confusing at the end, I apologize, was to show that trivialization, infinitesimal trivialization, means, for example, modding out by inner derivation. That's an example of infinitesimal trivialization. So something being inner.
That's a choice, right? I mean, in your previous example, you have endomorphisms of the Ram complex. You have endomorphisms of degree 0, endomorphisms of degree -1.
Yes.
You have a differential, so you have a built-in notion of what it means to be trivial.
Yes.
Homotopy. So here you're defining such a notion.
No, I've given an example of it, now I'm defining it.
Okay.
So definition. So actually there's a preamble to the definition. So the preamble says, the preamble is that G acts on the category C, and it acts at least differentiably, so we can talk about the Lie algebra. Then, as a consequence, G acts on C, and I'm going to claim G comes to the map to the Hochschild 1 cocycles on C. Induces a map on Hochschild 1 cocycles. Or rather to say, for this definition, in order to talk about differentiable action, I want some explicit model of Hochschild cochains so that the infinitesimal action maps G to HZ1. And recall that Hochschild cohomology is a Lie algebra after degree shift by 1. And H1 are the derivations of at least for an algebra, are derivations modulo inner derivations we had before. So that's what we're after now. So there's a Lie bracket actually on the Hochschild complex, so we're asking that is the Lie algebra map. And now a trivialization of the infinitesimal action is as before a factorization through the zero algebra, through and by this I mean the following. As before, you have G the same as G, and now you artificially make it 0 by putting a G in degree -1 in the identity differential. Now this must map to the Hochschild cocycles, and I'm asking now for a map to the Hochschild 0 cochains. This is the category C, I guess. So that this being the Hochschild coboundary, so that one. So this is a map of differential graded Lie algebras, and what I had forgotten last time, it is equivariant under the group. And in particular, we do require that iota psi and iota eta commute inside Hochschild cochain, so it's a condition on the trivializations now. And example, if C is just A modules, then the Hochschild cohomology of the Hochschild complex of C is quasi-isomorphic to the Hochschild complex of A, and it starts as A mapping to Hom of AA, and continuing to a map which guarantees that the cocycles are derivations. And this map sends an algebra element to a derivation which is a commutator. So before, by mapping the Lie algebra into the algebra U of G in the obvious way, I have trivialized the infinitesimal action. That was exactly trivialization data. So that's a definition.
If we want, can we think of an A model action as a B model action of G modulo G hat?
Yes. That would be the short way of saying it. If you're comfortable with that, you could say it's exactly a B model action of G mod G hat, but that already being a derived group you've pushed all the complexity in defining but yes, I mean, you know what to say. You have a sheaf of groups over not represented by an algebraic group anymore. You have a sheaf of groups, a sheaf of categories. No, it means to act, but that's correct. How are we doing with time? Okay, a familiar example is X is a topological space. X is a manifold, sorry. G acts, and you have, guess what? You have a differential grade algebra now. And G acts as before, so the same formulas give a trivialization of the action in the sense of algebra, an infinitesimal trivialization of the action. As DG algebra actions. So from here you might have a guess. Something like the quotient category. Quotient category should be actually no, that would be a fixed point category. Let's unlock to that, a fixed point category. Should be the Cartan differential form. Should be omega x tensor sim g star fixed by g with Cartan differential. After all, it's a DGA now. So you might think that the fixed point category for the G action would be modules over that. And this is actually false. And it's also related to twisted sectors. But there's a correction of this, which is true. I'll discuss it on Tuesday. So a correction exists. I can't discuss it today because it involves curved algebras to define it. It's called a curved Cartan complex.
So here, could you lower it? What's a category? We're looking at the category.
You could start the category of modules over this DG algebra, and you ask what is a fixed point category. In the first guess, you just form the Cartan complex that gives the DG algebra. Take modules over that, and that's usually not the fixed point category. Okay? You need to fix that a little bit. It's actually pretty obvious for a finite group, for example, that something goes wrong. So G equivariant A modules are not the same as modules of a fixed point algebra for a finite group. That's a very easy exercise, so that's a mistake essentially. But there's a correction. It's miraculous, an easy correction. So I don't want to discuss this today because it takes more material, and believe it or not, we've gone through a difficult part. It's getting easier from now. Let me define now the notion of the locally trivial action. And that's the one we'll be analyzing. Action. A locally trivialized action. And now I can no longer do what David was suggesting, modeling out by some group. I want to trivialize the action on neighborhood of the identity G. So it's a G action on a category. Action on a category, and trivialized on U containing 1, a neighborhood of 1 in G. And trivialized means you have natural isomorphisms from the action of a group element to the identity functor. So let's give them a name phi g for all g near 1, for all g in U, and these are coherent under multiplication whenever you can multiply.
So you require one open set for all objects in all groups?
I require, you can think of taking the limit as it doesn't matter. Once you require for some small open set, doesn't matter which small contractible open set you ask for, because basically you can now continue moving a trivialization on just by finite multiplication. And you might think actually that forces the action to be trivialized everywhere. To surprise, that's not true. So let's go on to the torus from now on. How are we doing it? Case of a torus, where things can be made explicit. So let's say we have so have T acting locally trivially on C. Let's assume that now. And now also have a very nice exponential map from the Lie algebra to the torus, which is a covering map, of course. Kernel pi, which is pi 1 of t. And here's the claim: the trivialization of the action can be continued coherently to all of t, to well, exp of t if you like. Because it's contractible essentially. I mean, it's the usual argument about analytic continuation along the path. If there's a homotopy between paths, they agree. That's how it's going to work. So this is the usual analytic continuation argument. So simply connect the version of the group acts. Okay, so is there any information left? Well, there is information left for the following reasons. So we look at, this is a torus T, sort of this is the Lie algebra sitting above it. So let's say this was a point 0 which maps to the identity. This is some other point P which maps to the identity. So we know this is the, so we know now, so the action of exp of rather let's say P in T is trivial for two independent reasons. Reason number one, it maps to the identity in T, and that acts as the identity. After all, the action factors through T. And reason number two, we've trivialized the action in the Lie algebra. So what, as I said in the category, if you do nothing twice, you're doing something. So from the two trivializations of the action, you get an automorphism of the identity functor of C. And this is a group homomorphism, in fact. So if you prefer, C of pi, which is a group ring of T, maps as a ring to the endomorphism of the identity functor of the category, which some people don't know as the center or HH0 of the category. And I should add, it won't matter in this case, it will be an E2 homomorphism, but let's ignore that. Now, the picture you want to keep in mind is being the center of a category. An algebra sort of fibers over its center. You can localize it over its center. A category, similarly, you want to think it fibers over a spectrum of its center. So, since the center now maps to spec of this, get a sheafification for free of the category C over spec of C of pi, and that is the dual torus. So the original category is C fibers over a dual torus. That's exactly the information you can extract from the action of the torus, locally trivial action of the torus on the category. So the action is captured by a, how are we doing? Fibration, or sheafification, let's say, fibration or sheafification of the category C over T check.
That means, just from that map of rings that you had.
from that map of rings. Or equivalently, you can also say that C becomes, if you prefer this formulation, a module category over the tensor category of coherent sheaves on T-check. Now, an example of such a things, if C was equivalent to the category of coherent sheaves on some, let's say, Y, then a holomorphic map or an algebraic map, let's say, a map from Y to T check would provide such a structure. So let's start with mirror symmetry. Let's start with X be a compact symplectic manifold. Oh, okay. Oh, I'm sorry.
This is a good break.
I wasn't.
No, do this if you don't mind.
Yes. Well, I'm sorry. I've never even explained the rules about time. Compact symplectic manifold. All right.
Don't stop it. We know what that means.
Compact symplectic manifold, and T acts on X by Hamiltonian.
Even what that means.
By Hamiltonian, it's a Hamiltonian action. I always say it badly. T given a Hamiltonian action of T on X. Then some magic happens. I won't even try to explain. T acts locally trivially on the Fukaya category. So now if X has a mirror Y, then what do you expect? The holomorphic map from Y to T check. Maybe even algebraic if you're lucky. And if you have that, then this completely captures the action on the Fukaya category. Action on the Fukaya category of the action of T over X. Okay, so maybe that is a good point, because next I have some very nicely written notes with pictures about toric varieties spelling this out, and the connection JIT quotient. So we can probably do that this afternoon.
Any quick questions? Okay, great. So we'll resume it.
We'll have to